2025 A-Level Combined Mathematics Paper 2 Part B, question number 12, Part A. Part B of this same question will be discussed in a future video, link in the top right. Part A says, the vertical cross-section ABCDE through the center of gravity of a smooth, uniform block of mass 10 m is shown in the figure. The face containing AE is placed on a smooth horizontal floor. Also, AB, BC and DE are lines of greater slope of the faces containing them. It then says CD is parallel to AE, meaning the CD is also flat, and EAB angle is equal to ABC angle is equal to DEA angle is equal to pi by 3 radians. Three particles P, Q and R of masses 5m, m and m respectively are held on AB, BC and DE respectively. So we can see each of these particles are held on each of these faces. The particles P and Q are attached to the ends of a light, inextensible string passing over a smooth, light, small pulley fixed to the block at B. The system is released from rest with the string taut from the position shown in the figure. So basically, we have this position shown where the particle P is like this, the string is taut, particle Q is like this, R is like this and the block is like this, and we release everything and let physics do the rest. It then says, obtain equations sufficient to determine the acceleration of the block and the magnitude of the reaction on P by the block. Now, when it says find equation sufficient, it of course means that we don't actually have to find the exact values. We don't have to find the acceleration of the block, and we also don't have to find the normal reaction that is placed on P by the block. So all we have to do here is to just make a bunch of equations in terms of these variables that we can then later use in order to find the reaction here and the acceleration of the block. So to solve this question, what we generally have to do is to consider the situation that you have and draw pretty much every single force and acceleration on every single object inside of the image. And then when you do this, when you complete the entire set of forces on the system and the acceleration on the system, you can then start producing a bunch of equations that you can then use in order to find the values that you want. So in this case, we have this system. We have the ball P over here, the other one Q over here, we have R over here, we have the block ABCDE, which for convenience I'm going to say let X represent A, B, C, D, E, because I don't want to keep saying A, B, C, D, E, instead I'll say X. So the block is now represented by X. So given this, if we start considering the forces and accelerations involved, the block is either going to slide left or slide right. It cannot go down because it's going to have to go through the floor, and it cannot go up because there's no forces that would make it go up over the floor that it's on. So therefore, the acceleration of the block must be in the horizontal direction. So I'm just going to pick an arbitrary direction and say that the block is going to be accelerating in this direction, and let's say the acceleration is capital F or something. Now furthermore, if we consider each of the particles, since these two particles are attached by a light inextensible string and they're probably not going to bump off of this surface, we can say that if this particle accelerates down with a certain acceleration like this, like indicated by double arrows, then the other particle Q is going to accelerate up with the same exact acceleration. So I'm going to call this acceleration, let's say F1, simple F1, and this acceleration is also going to be simple F1. Now similarly, for this particle R, it's going to have downward forces, meaning it's going to slide down this slope that we have here, meaning that its acceleration is going to be down the slope like this, and I'm going to call that acceleration, let's say F2. Now after this, to mark all of the forces, we need to consider the weights and any frictions that are involved. Now in this case, since everything is smooth, there are no frictions, meaning the only forces that we have are going to be normal reactions and gravitational forces. So the block itself is mass 10 m, and each of the particles is mass 5 m, m and m. So therefore, if we mark all of those, we're going to have a downward force here, which I'll actually mark with the proper symbol of the arrow symbol. Downward force of 5 m here, and then for each of these particles, particle P is mass 5 m, so it's going to have downward 5 mg like this. This is going to have downward mg like this. This is going to have downward mg like this. There's also going to be a normal reaction here like this, which goes through the center of gravity. There's going to be a normal reaction here that goes through the center of gravity, and there's going to be a normal reaction here that goes to the center of gravity. Now similarly, due to equal and opposite reactions, there's also going to be a force at this point into the block like this, which is going to be equal and opposite. There's going to be a force at this point equal and opposite like this, and there's going to be a force equal and opposite like this. And also from the ground there's also going to be another reaction force upward on the block like this. Now here you might notice that some of these surfaces are not touching each other. For example, this ball and the surface AB are not touching each other. Now the reason I've done this is to clearly indicate that this force is acting on the block and this force is acting on the ball. So if that's confusing to you, that's why I've marked them like this. So I hope you understand why they're marked like this, and we can move on. So same thing with the ground, of course. I want to indicate that the normal reaction is acting on the block by the ground. So I've marked it with its arrow starting from the block and not from the ground. Now additional to this, since we have a string here, there's also going to be a tensional force in the string, which I'm going to mark like this. I'm going to call this force T. Same force will be here. We don't really need to mark this one, but I'll mark it anyway. It's going to be same force T here and the same force T here. Now as for the rest of the forces, downward gravitational force here is 10 mg. Here, since particle P has mass 5m, it's going to be 5 mg. Here it's going to be Q has mass m, so it's going to be just mg. Here is going to be again mg. And then as for the normal reactions, let's call each of them, we'll call this one capital R sub P. We'll call this one, capital R sub P. We'll call this one capital R sub Q since it's on Q. This is also capital R sub Q, but in this direction. This is going to be capital R sub capital R. This is going to be capital R sub capital R. And this normal reaction here we'll call it SO something. Now in reality, when you're actually solving this, in order to find the things that they've asked us to find, we don't really need to mark this force, or this force. We only really need to consider this force in order to find the equation that we want. But we need these forces as well, because when we're considering the total block involved, we might need these forces in order to find the total forces involved in the entire system. But for now, we'll just mark them anyway. We don't really need this S force either, but we'll mark it anyway again, as I keep saying, just so that our diagram is complete. So now at this point, if you consider the diagram, we marked all of the forces on this block. We marked the acceleration on the block for particle P. We mark the forces on particle P, this force, the tension force and the downward gravity, and the acceleration of P. Since the string is light and inextensible, any acceleration on this particle in the downward direction like this is going to be experienced by this particle in the upward direction. This particle also experiences RQ, downward gravity of mg, and tension. And as for R has also been marked. We have mg downward, R sub R here, R sub R up here, and a different acceleration F2 in this direction. So now, even though we marked all of these, we will still need to define them, because even though we know exactly what each of these variables are, the rest of the world, including the examiner of course, does not know. So if we mark them, we can start by marking the accelerations. Let's say, let the acceleration of the block, which is x, relative to the earth, be equal to f in this direction. Let the acceleration of, let's say P, will do P relative to x, be equal to F1 in this direction. And then let the acceleration of the next particle involved is Q in upward direction. So Q relative to the block, so Q relative to x, be equal to F1 in the upward direction like this. And then the acceleration of the last particle rather, which is R, with respect to the block x, be equal to F2 in the downward direction. Now if we wanted, we could also mark the angles here. In this case, this is pi by 3, then the angle here is also going to be pi by 3. So we can mark like this. We can mark something like this. We can call this angle here pi by 3. If we want to be precise, we don't really need to do that part. But if we want to be precise, we can mark it. So then this angle here is going to be pi by 3. And finally, considering this one, that angle is also going to be pi by 3. So this angle is also pi by 3. So there we go. We marked out the accelerations. Now additionally, I'll also name RP, RQ and RR, because it's not really, it's clear from the diagram, but it's not really clear to whoever is watching what this might be. And I'll also define T. So we'll say RP be the normal reaction on P, RQ be the normal reaction on Q, and r sub r be the normal reaction on r and T be the tension, we'll just say, in the string. So now that we defined all of our accelerations and forces, we can now apply F equals ma in different directions in order to find a bunch of equations that we will then be hopefully able to use in order to finally find what the normal reaction Rp here is and the acceleration F here is. Now when applying F equals ma, the first thing that I'm going to do, and likely the first thing that you're also going to do when you're faced with a similar question like this, is to first apply F equals ma for the entire system. Now the reason I say you're likely to do this, and the reason that I say you probably should do this, is because considering F equals ma, if we apply it to the entire system, you can see in each of these objects here, there is a force and an equal and opposite force internally. So within any two objects within a system, there's going to be equal and opposite forces, which means that they're going to cancel out. This is Newton's third law. So due to this, within a system, if you apply F equals ma, the only forces that you have to consider are external forces. You don't need to consider any internal forces, because internal forces will always cancel out when you do F equals ma. So due to this, you are going to have only a few forces to consider when you apply F equals ma for the entire system. Now in this particular case, if you consider the horizontal forces in the horizontal direction and you apply F equals ma for the entire system, you will notice that there is not a single horizontal external force on the entire system. So due to this, when we apply F equals ma, if we go down and say applying F equals ma, and we apply F equals ma for the entire system, so we say for the system, if we apply F equals ma in the horizontal direction like this, then on the left hand side, for the sum of all of the forces F, we're going to have 0, since there are no external forces acting on the system. Now, considering the accelerations and the MAs, what we need to do on the right hand side of the equation is to add all of the individual MA components relative to the Earth of each of the individual objects within the system, and all of them added together is going to be equal to 0. So what we're going to do now is to go up and consider each of the objects within the system, find their MAs, add them all together, and write that on the right hand side of the equation. So here we can see for this system we have 4 objects. We have the block X, we have the particle P, the particle Q, and the particle R. If we first consider the block X has an acceleration of F in the rightward direction, and it has a mass of 10 m. So therefore the MA component in the rightward direction is going to be 10 m capital F. Now if we consider next, let's say P, for the particle P when we're considering horizontal direction, since the particle P has an acceleration of F1 in the downward direction like this, relative to the block, what we need is the horizontal component of that acceleration, which means we need to find this length right here. So considering the angles, if this angle is pi by 3, this angle is also pi by 3, meaning what we want is the cosine of pi by 3 component of F1. Now since we're considering all of the forces and accelerations in the rightward direction as positive, this is going to be a negative acceleration, to be negative F1 times the cosine of pi by 3. Now that is the acceleration in the horizontal direction of the particle P relative to X. But remember, we also have an acceleration of X relative to the Earth of F. So due to this, we need to add both of these together when we find the final acceleration. Now since this is negative, when I go down and write down the acceleration, the mass of the object P is 5m, so I write 5m times, and for the acceleration I'm going to write capital F, which is the acceleration of the object X relative to the Earth, plus the acceleration of the object P relative to X, which is in the negative direction. I'm going to write as minus, and it's minus F1 times the cosine of pi by 3. So we have the cosine component of pi by 3. Now I could simplify this to equal to half, since the cosine of pi by 3 is half, but I'm going to leave it as cosine of pi by 3. Now then, moving on to the next object, we need to next look at Q. If we look at Q, Q has an upward acceleration in this direction of F1, but again we need the horizontal component, so here we need this component right here. If we consider the angle, this is pi by 3, meaning we need the cosine component, so we need cosine pi by 3 times F1. It's in the negative direction, so we have negative F1 cosine pi by 3, and that of course is the acceleration of Q relative to X, so we need to add to that the acceleration of X relative to the Earth, which is going to be F. So we need to have a final term of m times, m is the mass of Q, times F, and since we have plus a negative number, we're going to write that as minus it is f1 cosine of pi by 3. Now finally we need one more force and one more ma value. The final ma value and acceleration we need to consider is going to be that of r, and for r we have downward acceleration of f2 like this. What we need is the horizontal component, so we need the cosine value. Here we can see this angle is pi by 3, so this angle is also going to be pi by 3. So we need the cosine component of pi by 3, meaning we have f2 cosine pi by 3. Since the rightward direction is positive, that f2 cosine pi by 3 is actually positive, and to that we need to add f, since that acceleration of f2 cosine pi by 3 is r relative to x, and we need to add to that x relative to the earth, which is f. So therefore the overall acceleration is going to be plus m multiplied by f plus f2 cosine of pi by 3, and that we're going to call equation number 1. Now after this we need to apply f equals ma for the other objects to get a bunch more simultaneous equations that we can eventually use in order to find the values that we want. As a reminder, the values that we want are rp and f. Now considering this, we have 3 more objects that we can apply to. We have p, we have q, and we have r. We could also apply to this object here, we could apply to x, but considering x in the horizontal and vertical directions, we are only going to get equations with rp, rq, and rr, and mg's, and this normal reaction here. Not really that useful. So for that reason, we're going to ignore the forces on x and only consider p, q, and r for our next equations that we're going to create. So considering p, we could apply in the downward direction down the slope or the perpendicular direction like this. Now considering these two directions, this direction is going to give us a relationship between t, this component of mg, and the acceleration f1. And in this direction we're going to get rp, which we do want. So therefore we're going to apply for both the downward direction and the perpendicular direction for the particle p, since both of them give equations that we can use in order to find things that we want to find. So what I'm going to do next is to apply f equals ma for p, and we apply 4p down the slope. So I'm going to mark the angle as pi by 3 here to indicate it's down the slope, and then I'm going to again apply it 4p, but this time I'm going to apply it in the direction perpendicular to slope like this. I'm going to mark it like this, and this angle I'm going to mark, we can mark this angle as pi by 3. Now, considering down the slope, if we go up here and consider down the slope, we have a force of t, but that force of t is going up the slope, so it's negative. We also have mg component in this direction. If we consider the angle here, it's going to be the sine component, so we have 5mg times the sine of pi by 3 downward like this, and then considering the other force rp is perpendicular, so it doesn't actually contribute anything. So therefore the only two forces we have here are the 5mg sine component and negative t. So if you go down and write that, we have down the slope 5mg sine pi by 3 and minus t, and considering ma on the right hand side, we have a mass of 5m, so we have 5m, and considering the acceleration, we need to find the acceleration relative to Earth, but what we have here is the acceleration of p relative to x in the downward direction. To that we need to add the acceleration of the object x relative to the Earth in this direction. If we consider the acceleration that we have, it's f in this direction. So what we need is, given this f, to find the component in the upward direction like this. Now if we consider the angles involved, since this angle here is pi by 3, we can see that this is also going to be pi by 3, meaning if we consider the components that we have, the component of f that's going to be acting in the upward direction here is going to be f sine of pi by 3. So therefore we have f sine of pi by 3. Since this line here is going to be parallel to this line right here, we have an angle of pi by 3 at that point, meaning that this angle here is pi by 3, so we have pi by 3 here, meaning that the component we want, this component, is going to be f cosine of pi by 3. So therefore the component of f we have is f cosine pi by 3, but you'll notice that f is acting up the slope, and we consider down the slope as a positive, meaning that that actual acceleration is negative. So we have f1 in the positive direction minus f times the cosine of pi by 3. So if we go down and use this knowledge and we consider the acceleration, we're going to have f1, we're going to have here f1 minus capital F times the cosine of pi by 3. And that's going to be acceleration for this thing. So we have this thing, which is going to be equation number 2. Now after that, if you consider P in the perpendicular direction to the slope, which is going to be in this upward direction right here, the forces that we have are Rp, and this component of mg in this direction is going to be mg cosine of pi by 3. So we're going to have Rp. If we consider this is the positive direction, we have positive Rp, and if this is the downward negative direction, we have negative 5 mg times the cosine of pi by 3. So writing that down, we have R sub p minus 5 mg cosine of pi by 3, and those are all the forces. Since all other forces are perpendicular or not relevant, this T is perpendicular and this component of the mg force is not relevant, so you have only those. And then considering the accelerations, since F1 is down the slope, the perpendicular component of F1 is 0, but this F still has a component. Now if we consider the component, since in the last one we had the cosine component, cosine of pi by 3 in this direction, in the perpendicular direction, which is this direction, we must have the sine of pi by 3. So therefore, considering the accelerations involved, we have Rp minus 5 mg cosine of pi by 3, which is going to be equal to 5m times the acceleration, which in this case, since we are accelerating in this direction, but f is going to have a component in this direction, it's going to be negative, so we have negative f times the sine of pi by 3. So we're going to write minus f sine pi by 3, and this is going to be equation number 3. Now that we've done all of the equations for P, let's move on to the next equations that we're going to create, which is going to be the equations from Q. Now considering Q, if we do it in this direction, which is perpendicular to the slope, we're going to get RQ, but since we don't want RQ, we don't actually have to do this. Instead, we can just take parallel to the slope like this. So considering this one, we're going to have another relationship between T, F1, there's also going to be mg in there, there's also going to be f in there, so that we can do. We're also after this going to consider r, and for r as well, since we don't want the normal reaction, we're not going to do it in this direction, we're only going to do it in this direction. So now, if we go down and consider that, for q, if we go down here and say, for q, what we're going to do is do up the slope, so like this, and the angle here is pi by 3, I believe, so here we have pi by 3. And then, if we apply like that, we can see in that direction, we have a force of T like this, so plus T. And then we have a minus mg is this component. Since this angle here is pi by 3, this is going to be minus mg times the sine of pi by 3. And this force is not relevant, RQ is perpendicular, but we have an acceleration of F1, which we're going to consider later, and also the acceleration of F's component in this direction. So going down, if we write all of that down, we have a positive tension component, so plus T, minus mg times the sine of pi by 3, and that's all the forces that are relevant. And the acceleration is going to be with respect to m, since m is the total mass that we have, times the acceleration, which if we go up, we can see we have a positive f1 up the slope, but then we have this f's component down the slope. Since this angle here is pi by 3, if we consider the components, we have f like this, but what we want is this component like this. The angle here is going to be pi by 3, since this angle is pi by 3. So therefore this is pi by 3. If this is pi by 3 and we want this component, we want the cosine of pi by 3. So you have f cosine pi by 3 in the negative direction, which means we have minus f cosine pi by 3. So you have plus f1 minus f cosine pi by 3. So if we go down and write that, we have m f1 minus capital F cosine pi by 3. And this is going to be equation number 4. Now, as we discussed, we don't really want to do the perpendicular direction, so we're going to go directly onto r. So we're going to do 4r, and for r, we're going to do it in the direction along the slope. So we're going to do it in this direction, but since the accelerations are all in the downward direction like this, I'm going to consider this direction as the positive direction. So doing that, I'm going to write it as this direction, where this angle is pi by 3. So considering this direction, if we consider the forces involved, we have, actually we only have one force. We have the mg component in the downward direction like this. Since this other force is perpendicular, it's not relevant. So we have mg is this direction force. Since the angle here is pi by 3, we have mg sine pi by 3. So we have mg sine pi by 3 being the only force. So we have mg sine pi by 3 equals, on the right hand side we have m multiplied by the acceleration, which if you write down the acceleration, we have full F2, and then we also have the component of the capital F acting down the slope, which if you consider the angles involved, we have this component that we're looking for. The angles here are, well, this angle here is going to be pi by 3, which means that this angle is going to be pi by 3. If we want this component, we need the cosine component. So once again, it's f cosine pi by 3. So we have f cosine pi by 3 acting downward with the f2, meaning we add the two together, which means if we go down and write that down over here, we have f2 plus f cosine pi by 3, and that is going to be equation number 5. Now, if we consider these equations, we pause for a moment and consider the equations. Each of these equations have the unknown variables f, which is 1, f1, which is 2, and then f2. So we have 3 unknown variables. We then also have in this equation t, and in this equation rp. If you look at the rest of them, we again have t, rp, all of that. So we have a total of 5 unknowns. And if you take a look, we can see we have a total of 5 equations as well. We have to assume, of course, mg unknown. So we have 5 equations and 5 unknowns, which means that these 5 equations are all that we need, since out of the 5 unknowns, capital F and rp are the unknowns that we want. So since all of these equations are non-similar, meaning that no two equations are duplicates of each other, we can say that these 5 equations, 1, 2, 3, 4 and 5, are actually sufficient to find the acceleration f and the value of rp. So we can say finally that the equations 1, 2, 3, 4 and 5 are sufficient to determine we wanted f and r sub p. So it's sufficient to determine f and r sub p, and that is actually all we have to do. Since if you recall in the question, it said find equation sufficient to determine the acceleration of the block and the magnitude of the reaction on p by the block. So we only need those two only, which means we have already done what we need. We have determined find the equation sufficient to determine those two, which means that we are actually done with this question. So that's going to be all for this question. Now finally, let's discuss the marks awarded for this question. So at the start of the question, when you're drawing all of the forces, when you identify that the two particles P and Q will have the same exact acceleration but in different directions, and you identify the directions correctly, you get 5 marks. After that, when you draw all of the forces, you get 5 marks for all the forces being drawn correctly for the particle P. You get 5 marks for all the forces being drawn correctly for the particle Q, and you get 10 total marks for all the forces drawn on the block, which I called X, but A, B, C, D, E if you like. All of those forces being marked correctly, of course, gets you a total of 10 marks. Now after marking all of the forces like this, when you then go to making equations, for the first equation where you apply for the system, for each of the individual components of MA that you have 0 of course, and then you have MA of the block, MA of P, MA of Q and MA of R. For each of those MA components, you get 5 marks each. So 5 marks here, 5 marks here, 5 marks here and 5 marks here. And then if you get the entire equation right, including the equals 0 part here, you get another 5 marks. Now after that, when you apply F equals MA for P, for the P down the slope you get 10 marks. For P in the perpendicular direction you get another 10 marks, and then for Q down the slope, actually no, not down the slope, rather up the slope, you get 10 marks. But for R, when you apply down the slope, you get only 5 marks. And the reason for this is of course because R has less forces involved, so it's less difficult to do. But still, you get 5 marks. So that's going to be all for this question. So I hope you enjoyed. If you have any feedback, post them in the comments down below. Thank you for watching and goodbye.